Hi guys, so today's work is about Hooke's law, which is all to do with the springs. So I've got this image here of a big monster truck, and here you can see the springs. It's really important in the design of springs that you make them springy enough for what you want them to do, so in this case suspension, but also tough enough and stiff enough so that they return back to their original shape in the time that you want them to. If these were not stiff enough, then the car would be lower, okay, and when it went over a bump, it would also continue to bump up and down. So yeah, the design of springs is really, really important. So what Hooke said was that the extension of an elastic object, such as a spring, is directly proportional to the force applied, provided the limit of proportionality is not exceeded. So let's break down this sentence a little bit. The extension of an elastic object, such as a spring. So if you're extending a spring, okay, you're pulling it apart, is directly proportional to the force. So that means if you've got a spring and you put a little bit of mass on it, it'll move a little bit. If you double the mass on it, then the extension will double. If there's no mass on it, then there's no extension. And then it talks about here the limit of proportionality. All the limit of proportionality is when if you stretch a spring too much, it remains unstretched and then can't be used, and we call that deformed. So if you were to apply this statement to a graph, so if you had a spring, you applied a stretching force, so you're increasing the force step by step. The extension would also increase, and in fact if you double the force, the extension would double. That's what directly proportional means. It also means that if there's no force, there's no extension, so your graph would go through 0, or the origin, which is here. So if you're looking for a graph that's directly proportional, you look for it to go through the origin and then be a straight line, where if one thing doubles, the other doubles. And a really good technique on higher questions is, if they ask you to describe the graph, is then to use numerical values from the graph to prove that it doubles. What you'll notice at the end here is that the graph curves over. What that means is for the same force, or a tiny increase in force, you're getting a very large extension. That means that the limit of proportionality has been exceeded. So we call that the elastic limit, or the limit of proportionality. It's reached when the graph of the line starts to curve over here. Now this is the equation that goes with Hooke's law. It's this statement but in equation form. So we've got the force measured in newtons with the symbol F is equal to something called the spring constant. The spring constant is literally how stiff the spring is. So if it has a high spring constant, it means that the spring is very stiff, and if it has a low spring constant, it means it's really, really easy to pull apart, okay, and extend. And then you've got the term E for extension, measured in meters. You can do it in centimeters, okay, as well, but your force wouldn't then be in newtons. Here's a triangle. So if you use the triangles, if you wanted to find force, you'd cover the force up, okay, and then it would be K times E. If you wanted to find K, it would be F divided by E. If you wanted to find E, the extension, it would be F divided by K. So here we've got some different types of spring here. This is a spring on a trampoline. It's fairly stiff, okay, and it would extend as you jump up and down. This is a slightly different spring. This is a pogo, and actually a pogo spring would, rather than extend, it would compress. So the equation still works for compression. It just refers to the extension or compression of the spring. So it's just the change in the original length of the spring, whether that's getting larger or smaller. The equation still applies. Now, this sort of topic comes with a practical investigation, which you obviously can't carry out right now, but if you click on the computer emoji, it'll take you to a video of the practical. But the aim of the practical would be to find out the relationship between force and extension for a spring and use it to calculate the spring constant. So this is the apparatus that you would use, and we will do this when you come back. Is you have a table, clamp, okay, and on it you hook a spring and you add a mass. And here you've got a ruler. So what you do at the start is you measure the original length of the spring when it's got no masses on it. You then add masses to the bottom, increasing in mass here. So a good suggestion there would be adding 100 grams at a time. You would then calculate the weight of that. So 100 grams is 1 newton. So 200 grams would be 2 newtons and so on. You would then measure and record the extension, which is the difference between, we've added a mass here, so this length here would not be the extension. The extension would be the difference between this length here and then the original length of spring without anything on it. Okay, so that's the extension there. What you then do is plot a graph of weight against extension, and as you can see we've got a beautiful straight line here that goes through the origin, so it shows Hooke's law where force at the extension of the spring is directly proportional to the force, okay, because it goes through the origin. If we take some numbers, a force of 2 newtons gives you an extension of 0.04 meters. If we double that to 4 newtons, we get an extension of 0.08 meters, so that's double. If we have a look at this equation then, force is spring constant times extension, which we had before. If we wanted to find the spring constant, K, using the triangle before if you need to, that would be the force divided by the extension. And that is actually the gradient of the line. Gradients are the change in y over the change in x. So if you look at what's on our y-axis here, we've got force, and on our x-axis we've got extension. So if we work out the gradient of the line, which is the steepness of the line, we'd be doing the force here, which is 10, divided by the extension, which is 0.2. And that would give us our spring constant. So if we did that, so we do the change in the force, so that's here, 0 all the way up to 10, so that's 10, divided by the extension, which goes from 0 to 0.2, so we're doing 10 divided by 0.2, that gives us 50. So the stiffness of this spring is 50 newtons per meter. That would mean that if you wanted to stretch your spring 1 meter, you'd have to add 50 newtons to it. If we had a spring of 25, that would be less stiff, so easier to move, and if we had a spring of 100 newtons per meter, that would be more stiff and more difficult to move. We can also work out how much energy is stored in the spring, because when you pull or stretch a spring, you do work on it, you make it move. And so that energy is stored. If you wanted to then release that energy, you'd let the spring go. We call that type of energy that's stored in springs and elastic materials elastic potential energy, and we define it as the work done by a force to stretch or compress a spring. All that means is how much energy do you have to put in to make it stretch, okay? And the work done on a spring is equal to the elastic potential energy. So how much energy you put in, okay, is then stored in the stretched spring, ready to be released when you let go. This is the equation for elastic potential energy. It's a little bit more difficult than the one before, although if you take your time with it, it's fine. So elastic potential energy is 0.5, so a half in your calculator, 0.5, times the spring constant, which was K, times the extension, but this time it's the extension squared. Okay, so if we had our table here and we were doing this practical, what I would then get you to do is work out the elastic potential energy here, but you can have a go at that on some exam questions, okay? You can also figure it out by doing the area under this graph. So if we have a look at this graph, we can see it's a triangle. So the areas of the triangles are half times the base times the height. So let's do that. Let's do a half times the base times the height. So 0.5 in my calculator times the base, which goes from 0 to 0.2. So 0.5 times 0.2 times the height, and the height is 10. So times 10. So I've done 0.5 times the base, which is 0.2, times the height, which is 10, which gives me 1. So I know that there is 1 joule of energy stored in this graph here, in this spring. 1 joule of energy. Okay, just as the last bit, I have talked about this, but we have a bit at the end of this spring where it no longer obeys Hooke's law, so it's bending. There's the limit of proportionality. This region is where Hooke's laws is obeyed, so the force is directly proportional to the extension, so you can apply the equation. After this, where it starts to bend, we call that plastic deformation. Plastic deformation. The spring will no longer obey Hooke's law, so you don't get this nice straight line. Okay, if you were to unload the spring, it would be a longer length than it started. Okay. And at some point the spring will actually break. In this section, the linear section here, you can use Hooke's law. In the non-linear section, you cannot use Hooke's law. And we call this region the elastic region and this region plastic deformation. Okay, so I'm going to set some exam questions now. I want you to have a go at them. Bronze question 1, silver question 1 and 2, gold question 1, 2 and 3. There's a help button within the virtual classroom. You can click on that and there'll be some ideas for you to get some additional help if you need it. For yourself first and then working through and then maybe contacting your physics teacher. Okay, thank you for listening.